For over a century, we've basically just looked at the universe through telescopes. But what if we could listen to it? What if we could actually hear the echoes from the most extreme, most violent events in the cosmos, not with light, but through the very fabric of space-time itself? Well, today, we're going to dive into exactly that. And I mean that literally. What if a collision between two black holes, maybe a billion light years from here, could send a signal that reaches us, like a sound? This isn't some sci-fi movie plot. This is the new frontier of astronomy, where we're using these ripples in spacetime, what we call gravitational waves, as a totally new sense to explore the universe. So to get how this works, we've got to go back to Einstein. His big idea, general relativity, tells us that gravity isn't really a force pulling things together. Instead, massive objects actually warp and curve the fabric of spacetime around them. Other objects just follow those curves. So when something truly massive happens, like a dying star collapsing into a black hole, or two of those black holes smashing into each other, it doesn't just create a flash of light. It sends out these incredibly powerful ripples through spacetime itself. And wow, this has been a long time coming. I mean, Einstein predicted these waves way back in 1916. We saw some indirect proof in the 70s, but it wasn't until 2015 that the LIGO Observatory finally made the first direct detection. And that brings us right up to now. A decade after that first groundbreaking signal, a new one called GW250114 has arrived. And thanks to some absolutely incredible leaps in technology, it is the clearest sound we have ever heard from the universe. So what exactly did we hear? Well, it turns out when two black holes collide and merge, the brand new combined black hole does something pretty amazing. It rings. Yeah, a black hole merger happens in three basic stages. First, you've got the in-spiral. That's them circling each other, getting closer and closer. Then, boom, the merger itself, a really violent collision. But the part we're really interested in today, the part that holds all the secrets, is that final step, the ring down. This is when the new, kind of lumpy, distorted black hole literally quivers and vibrates, shaking off all its imperfections to settle down into a perfect sphere. Keith Mittman over at Cornell describes it perfectly. He says the new black hole vibrates, much like a struck bell. And look, this is not just some poetic metaphor. It is a precise physical description. Just like a bell has its own characteristic sound, a ringing black hole sends out gravitational waves at very specific frequencies and decay rates. It has its own unique cosmic tone. And this really shows you the incredible leap forward we've made. The event that caused this new signal, GW2515, was basically identical to the first one we detected back in 2015. So what's the difference? A decade of relentless, brilliant engineering. We have made our detectors so much more sensitive that what was once just a faint whisper buried in noise is now a clear, distinct tone that we can analyze in stunning detail. All right, for all you engineers watching, this is where things get really cool. We're going to translate all this astrophysics into a language you know really, really well. We are basically doing spectroscopy on a black hole, but you can think of it as a classic system analysis problem. Just think about it this way. The black hole merger, that's your system input, your impulse. The gravitational waves that ripple out from it, that's the system's response, the output. The analysis that we're doing, what physicists call black hole spectroscopy, is just system identification. And the key metrics, the things we're actually measuring, the oscillation frequency and the damping time of that ring down, those are directly analogous to the poles of a system's transfer function. We're literally characterizing the fundamental properties of a black hole, just like you'd characterize a circuit or a mechanical system in the lab. So, here's the crucial test. A black hole doesn't just ring with one single tone, it has multiple overtones, kind of like a guitar string. Now, according to general relativity, every single one of those tones has to correspond to the exact same final mass and spin. Before now, our signals were just too noisy to pick out these different tones. But with the incredible clarity of GW2015-014, we measured two distinct tones. And guess what? They both pointed to the exact same mass and spin, confirming Einstein's theory with a confidence level of 99.999%. It's just a perfect match. So, Einstein was right. Again. Case closed, right? No. Not even close. Actually, this perfect confirmation is exactly what has scientists so excited, because now the real hunt begins, the search for where the theory might actually fail. It kind of sounds like a paradox, doesn't it? Why would you work so hard for decades to prove a theory is spot on, only to immediately start looking for cracks in it? Well, it's because the biggest mysteries in the entire universe, they're hiding right inside those potential cracks. See, here's the fundamental problem at the heart of modern physics. We've got two absolutely magnificent theories that describe our universe. General relativity, which governs the very large, planets, stars, galaxies, the whole shebang. And quantum mechanics, which governs the very, very small, atoms, particles. The problem is, they just don't work together. Where they're supposed to overlap, the math completely breaks down. There has to be a deeper theory out there, a theory of quantum gravity that finally unites them. And that is why we are listening so incredibly closely. If we ever detect a black hole ring down where the tones don't agree, a wrong note in that cosmic bell, it would be absolutely revolutionary. It could be the first tangible clue to quantum gravity, a hint about dark matter, or the very first piece of evidence that tells us we need a completely new theory of gravity. It would be the start of a whole new chapter for physics. But to find those incredibly faint wrong notes, we're going to need to listen even more carefully. And that means we need to build a much, much better ear. This is truly one of the greatest engineering design challenges of our time. And the scale of this challenge is just immense. The next generation observatory on the drawing board, called the Cosmic Explorer, is planned to be 10 times larger than our current LIGO detectors. This isn't just an upgrade, it is a monumental leap in capability. You see, building something like this means pushing every single field of engineering to its absolute breaking point. We are talking about designing sensors that can measure distortions in space-time that are smaller than the width of a proton. It means eliminating noise from every source you can possibly imagine. And it means writing software smart enough to pull an impossibly faint signal out of that deep silence. This is the kind of quest that will define a generation of engineers. So, as we keep listening to the cosmos, we're not just confirming old theories anymore. We're searching for the very first note of a new song, the sound of a deeper reality. And the question that drives thousands of scientists and engineers every single day is a simple one. Will the next cosmic bell we hear be the one that changes absolutely everything?